improper integrals. So last time we looked at integrals where the limits of integration might be plus or minus infinity. This time we're going to look at integrals which are not bounded on the interval. So for example, let's let f be a continuous function on the interval ab, except not at the point b. And let's suppose the limit as x approaches b from the left of f of x is either plus or minus infinity. Then we're going to find the integral from a to b of f of x to be equal to the limit as L approaches b from the left of the integral from a to L of f of x. If this limit exists, then we say the integral converges, otherwise the integral diverges. We'll do the same thing when we're on the case that f is continuous on the interval a to b, but not at the point A, and that we have the limit as x approaches a from the right of f of x is either plus or minus infinity. Then we'll define the integral from a to b of f of x to be equal to the limit as L approaches a from the right of the integral from L to b of f of x dx. And again, if the limit exists, we'll say it converges, and if it doesn't exist, we'll say it diverges. Now, if we're in the case where f is continuous on a to b except at some point c on the interior, then we will define f of x, or the integral from a to b of f of x, to be equal to the integral from a to c of f of x plus the integral from c to b of f of x. If both of the integrals on the right exist, then we'll say the integral on the left converges. If either of these integrals on the right does not exist, then we'll say the integral on the left diverges. So let's do an example. Let's look at this integral. This integral is not defined at x equals 1 because we get division by 0. So to solve this integral, we'll set up the integral as a limit. We evaluate the definite integral, and then we see what happens as L approaches 1 from the left. When that happens, this term's going to go to 0, and this term stays as 2. So we get that our definite integral converges and is equal to 2. Alright, let's look at another example. This time, if you look at the integral, you'll see that it's not defined when x is equal to 1, which is our lower limit. So to solve this, we'll set up our integral using limits. We then evaluate our definite integral. And then we look at what happens as L approaches 1 from the left. Well, actually, if we look at this first term here, this just turns out to be the natural log of 1, which is 0. So this is what we're trying to find the limit of as L approaches 1 from the left. To do that, well, here's the graph of natural log of the absolute value of x. The natural log of 1 minus L, or 1 minus x, is just a transformation of this function, and it looks like this. And you can see that as x approaches x approaches 1, coming from the left, the value of this function heads off towards negative infinity. So we find that that our definite integral in this case diverges. Alright, so here's one more example. Looking at this integral here, it's defined at both the limits of integration. However, it's not defined at x equals 2, which is in the interval. So what we're going to need to do is break this up into two integrals and then evaluate each one of those separately. So we break it up at 2, which is our offending point. We rewrite these two integrals using limits. We evaluate the limits, or the definite integrals, I should say. And then when we do this, we look at the limits. So for this first one, as L approaches 2 coming from the left, well, this term here is going to 0, and 0 raised to 1/3 is 0, so that's okay. And in this limit over here, as L approaches 2 from the right, again, I get this term right here goes to 0, and 0 to the 1/3 is okay. So we get that this is what our limits are equal to. So that means our integral converges, and converges to the value of 3 plus 3 times the cube root of 2. Here's another example. Let's figure out whether this integral converges or diverges. Well, okay, I know how to integrate that. I know that this integral, the antiderivative is this. I evaluate from 0 to 2. I plug in my points, and I get that this integral is equal to -2. But wait a minute. Look at the integrand. The integrand is 1 over something squared. That's always positive. And if you integrate something that's positive, you should end up with a positive answer. So I have done something wrong. And what I've done wrong is I've gone too fast, and I didn't stop and say, look at my integrand. Oh, it's not defined when x is equal to 1, and that's in the interval I'm integrating over. So that means I should have evaluated this as an improper integral. So I should have set up my integral and broken it up into 2 different integrals, used limits to rewrite those. Now I can go ahead and evaluate my integrals. And now look at the limits of these as L heads toward the appropriate place. Here, as L approaches 1 from the left, this is going to head off to either plus or minus infinity. And as L approaches 1 from the right, this term here is going to go to either plus or minus infinity. So that means neither of these limits exists. So since neither limit exists, that means our definite integral that we started with diverges.